president of Weihai Golden Solar. We are a producer of receiver tubes for line concentrators like parabolic troughs and Fresnel systems. We have a long tradition in making receiver tubes. Actually, my father started the solar business in 1972. He was an automation engineer that had graduated from MIT in the US. And in 1972, he started his first testing center for CSP. In 1992, he founded Solar Solar Systems together with us, with his sons. He built the first large Fresnel system in Solar Mundo in 1997. I founded Juha Ven in 2003 and founded Weihai Golden Solar in 2009. So we have been long-term in CSP. The other partner in the company is the Belgium-China Fund, and this is basically central government. It's the China Ministry of Finance, China Development Bank, State Development Bank and Investment Corporation, and the Belgian Ministry of Public Enterprises. So, why molten salt? And because my speech is about molten salt in receivers. If we look at the US at the moment, last year they did 60% of the new capacity was in renewables. And this creates instability in the network. The more PV is coming to the network, the greater the instability will get. And we see that on the load curve over the day. We see very fast ramp-ups that is needed for the additional plants that are installed. And so this will lead to inefficiencies of these power plants. There are a lot of free spinning capacities that needs to be available. And so that is where storage becomes important. And this is a part of the speech. So, direct molten salt and power plants, but why? Well, basically because we can run the salt directly through the receiver tubes. We can go to much higher temperatures instead of having a limitation caused by this thermal oil to about 400 degrees. We can take it up to 550 degrees. And the biggest effect of this is that the storage will become much smaller. It will become about 2.5 times smaller. Another effect is that we do not have any big pressure to keep these salts from evaporating. We don't have that. In thermal oil, you do have that. Thermal oil systems, they run maybe at 40 bar. Here, the pressure will be much smaller. It's just the dynamic pressure that we have to overcome. It has a few problems. It has freezing problems. And with freezing problems comes also, we have to prevent that, so we have to pump heat into the solar field overnight. And so the heat losses of this will become much bigger. So it also has a higher temperature, and that gives us a higher cycle efficiency. Yeah? And here we can see, if we look at just the cycle we had before, if we would take it to oil, we have a cycle efficiency of 37.7%. If we can take it to 550 degrees, we are at 42.4%. So this is a big increase in cycle efficiency. Of course, with higher temperature comes also a higher heat loss. And here is the formula completely written out of what this heat loss is. And it contains several important parts. It contains the radiation level, of course. It contains the concentration, and it contains the emissivity of the glass tube and, of course, of the steel tube. And it contains a factor which is the conduction losses in the vacuum system. You see here for one of our tubes the heat loss. So at 400 degrees we have a little bit more than 200. I think it's something like 220 watts per meter is heat loss. So if we look at it, there is a lot of things that we can do. We can lower the emissivity if we can by new coatings, but we can also increase the concentration ratio. This is one of the designs that we have been studying in the past, about 10 years ago. And this was using a secondary optics with a parabolic trough, and basically being able to double the concentration of the trough. If we have been analyzing that trough, we have built it actually. This is a picture of here. This was a collector that was 5.1 meter in aperture, a receiver of 40 millimeter. This gives you a concentration of 127, but you could easily bring it up. This doesn't need to be very accurate. This is a very inaccurate system. But if you would get the accuracy of modern collectors like the troughs that are being built now, you could probably get it up to 200 or something. Then the selective surface. The selective surface is basically a metal infrared reflector with on top of it an absorbing layer that has to be extremely transparent in the infrared region. And to get this absorption, what we do is we use a ceramic material that is doped with something metallic or a ceramic that has some properties of metals, like for example titanium nitride. On top of that lies an anti-reflective layer. The structure that you see here, high metal volume fraction, low metal volume fraction, was actually invented by a Chinese, Juha Ven, about 20 years ago in Sydney. And so what we can do with the selective surface is we optimize it for a certain temperature range. And you see in the graph, you see this optimization. You see that if we make it thinner, actually the absorption will go a little bit down. We might go down from 95.5 to maybe 95. But we can also lower the emissivity. So there is an optimization to be done in the selective surface if you go to higher temperature. There are limitations with the technology. So if we look at lowering emissivity, we can also use different metal infrared reflectors. Probably the best one is silver, but it's not easy to stabilize. Then after that will probably come aluminum, but that will not last much above 400 degrees. Then you have the molten, tungsten, and nickel comes then somewhere. So these are the materials that are available. If you would go to very high temperatures, you're going to find yourself with very exotic materials like platinum and stuff. There is a lot of conditions required on these materials. The total layer thickness of such a stack is only 300 nanometer. And so some of these coatings are something like 5 nanometers thick, so it's extremely, extremely thin. And so one of the problems is to block diffusion, make sure that all these layers doesn't start to mix together. We do that by diffusion barriers that we put in between all of these layers. And so core of the technology lies in the use of diffusion barriers that you put in these layers to block diffusion going through the other layers. We have our own development of sputter equipment, and here you see a sputter equipment that was made for making lab samples. And so what became very clear to us is that we had to be able to test very fast different type of selective surfaces in a very fast way. And so in this machine we can produce about every 20 minutes a sample, and this allows us to make thousands of samples. Now this machine has 16 targets, so we are able to do 16 different machines without breaking the vacuum, 16 different materials without breaking the vacuum. We have different power supplies, we have DC, RF, pulse power, we have electron beam. And so the whole range of methods, of deposition methods, is available in that machine. And with that we have been working, and we have been able to reduce a lot and improve a lot the stability of the selective surfaces. Currently we have 12 selective surfaces under evaluation, where we are looking at what are the better ones at a certain given temperature. The current receiver that we have now in the market has an absorption of 95.9, thermal emittance at 400 degrees of 7.8. It transmission of the glass color of 69.9 and a negative length of 79.8. So it is one of the better receivers on the market. And as was pointed out before, every percent point that you drop here in some of these efficiencies costs quite a lot of money. So it will cost you something like $1 to 1.8 million of investment for a 50 megawatt power plant. So it's very important, these numbers. Now if you look at the salts, because we are talking about salt, then there has been traditional, quite a few salts on the market. There has been the binary mix, and there has been this high-tech, and this high-tech XL. If we look at the binary mix, it has a pretty high freezing point. It freezes about 220 degrees. And to keep that fluid all over the night is not easy, certainly not in a situation like in China, where you have pretty cold winters, minus 30, minus 40, with strong winds. It's going to be difficult. So we do need a molten salt that has lower freezing points. Problem with this is, with these high-tech salts, is that they contain lithium nitrate, and it's not one of the nicest materials. This is a corrosion study that was done on high-tech XL with low amount of chloride and with a 316 titanium stabilized material. And we see that there is actually the corrosion that you have in these stainless steels is okay. It's not too bad. There are new salts on the markets that some has been developed in Norway, some have been developed in Germany, and that have a complete different melting point. They have melting points around 140 degrees, and with a reduced corrosiveness, and these are important factors in this field. If we look at these salts, then we can see that, and here stands the corrosion levels that each of these materials have. And we see that carbon steel, for a millimeter, it will take about 8 years to disappear. At 460, we see that, for example, 316 at 600, it takes 83 years for a millimeter to dissipate. So we have to look at various materials at various temperatures to minimize the cost of the receivers. And so if we look at the material specification, then we can see that if we have salts with chloride contents below 0.6%, and we think of a 30-year life expectancy, then below 400 degrees we can just use carbon steel. And from 400 to 480 we have to use low alloy steels, like a P22 or something. And then above that we have to use stabilized stainless steels. Now at Weihai we have quite a lot of experience in coating carbon steel tubes. We have been doing that. We have coated probably more than 140 kilometers of tubes in this, so we know what it is. It's not easy, but it's possible. Then a second point is on the welding of the receiver tubes. When we come to these high temperatures, then the heat affected zone of all of the welds that is going to be made, they will have to have some temperature treatment. We will have to heat them up again, post weld treatment, at about 800 degrees. So this might become expensive. To make sure that the chromium carbide dissolves again and that titanium carbide is formed. Then we have the getters is also important. So we have a solution that is serviceable. What we try to do is, from the beginning on, bring a possibility of opening the vacuum space and being able to work at it and close it after an operation, to close it off again. And you could do then many things. You could maybe replace the getters. You could maybe just fill it up with water. You could do all kinds of things to restore the functionality of the receiver tube. Important is also and this is going to be very important for molten salt, is getters and getter dust. Yeah? Getters are metals that are metal powders that are sintered, and once they get saturated, they become like powder. And this powder could go into the receiver tubes and fall on the inside of the glass and cause local overheating of the glass tube and cause breakage. And certainly at high temperature, when we have a receiver that operates at 550, this could be difficult. This could cause problems. Stress corrosion cracking is another thing in the bellows. It is stress corrosion cracking happens when thin or when stainless steel is exposed to high temperatures above 420 degrees. At that moment, the carbon is put out of the cells and can combine with the chromium that is protecting the grain. If that happens, you can get stress corrosion cracking. And this has been a failure mechanism that has been quite often in these type of receiver tubes. To avoid that, it is important that we keep the temperature of the bellows limited. Make sure also that there is no radiation that comes to any of these parts. And to limit the stress in the bellows. Some of the receiver manufacturers try to build maybe 2 or 3 wave bellows, but that actually increases the stress in the bellows and can cause later defects in the receiver tube because you overstress the bellow itself. So it also, we have to make sure that all of these bellows and all of these structures are clean, and that means that during the installation process, there shouldn't be any of metal parts or metal dust that enters into that cavity, and that could cause corrosion on the bellows. There has been also some problem with that. Okay, so I think that's my presentation. I thank you for your attention. If you have any questions,